Welcome. We're glad you could be here this afternoon on this historic day, and one that is especially significant here at Purdue. So I'm really looking forward to the program and learning a little bit myself. I guess it would be more accurate to call this the discovery of the transistor, because they were really doing experiments and trying to figure out what was going on, and in the process, the point contact transistor emerged. So this is, if you haven't seen this PBS series, I would encourage you to go and find Transistorized is the name of it. It's really excellent. And you can see how they're publicizing this particular series. You know, those of us who have worked in transistors all of our careers didn't know it was so exciting. You know, look at this. Bitter rivalries, clashing egos, top secret research, all the makings of a classic Greek tragedy. It really is quite a good video, so I'd encourage you to have a look. There's another one called Silicon Valley that's equally interesting. Okay, so yeah, this occurred 75 years ago today, and it was quite a significant accomplishment. The invention of the transistor, as some people call it, the most important invention of the 20th century, and it enabled everything that we see today. This is a famous Purdue alum. How many of you, the name Bob Lucky, yeah. He's really quite famous. He did his BS, MS, and PhD here at Purdue, and spent his career at Bell Labs and Bellcore and Telecordia, was a distinguished engineering alumnus and an honorary doctor. For years and years, he wrote an opinion piece in the Trade Journal for Electrical Engineers, IEEE Spectrum. It was never technical. It was always very thoughtful and interesting. In December 2014, near the beginning of the 21st century, he wrote this piece called Predicting the Great Achievements of the 21st Century. And he said, well, in thinking about what's going to happen in the rest of the century, he says we should look back to the beginning of the 20th century. And he said, in 1914, you actually could have foreseen much of what happened. Things that were already beginning to happen or that you could anticipate. The Wright brothers had flown. You could say you might be able to fly anywhere in the country or even across the oceans. Automobiles were there. There were roads. You could say you would have interstate highways that would connect everyone. So he said there's a lot of things you could have anticipated. There were a few homes that had electricity. You could say every home in the country would have electricity. But he said there are a few things that no one ever could have anticipated. And among that short list was semiconductors and integrated circuits. Nobody could have foreseen that developing. I tell people it's almost impossible to overstate the importance of this technology. Although Isaac Asimov, this famous science fiction writer, may have come close. So he describes something as the most important moment since mankind has emerged as a life form. And can you guess what that was? He was talking about the invention of the planar process. So this is a manufacturing process that was devised first to make better transistors, and then very quickly became the way to make integrated circuits and put multiple transistors on a silicon chip. And this really changed everything. All right, so we're going to begin today with a few opening remarks by Senator Todd Young of Indiana. He's not here in person, but he's going to be here virtually. Senator Young was co-author of the Chips for America bill, and you can see him at the signing of that bill last August. He's the person directly behind President Biden. So we'll begin and see if we can play this video.
Senator Todd Young here. I apologize that I cannot be with you in person today, but I'm grateful for this opportunity to be a part of today's celebration. I'd like to start by welcoming Bell Labs to Purdue University. You should know when I'm in Washington or traveling around Indiana, I find myself talking about Purdue a lot these days. That's because Purdue is on the forefront of a revolution in higher education and innovating far beyond what anyone imagined was possible even a decade ago. Because of the partnership between Bell Labs and Purdue, The world of technology was revolutionized by the transistor 75 years ago. Today, the transistor is called the most important invention of the 20th century. With recent investments made by Purdue in research and development, I'm confident that the spirit of innovation will not fade anytime soon. I'm looking forward to what the next 75 years will hold for the semiconductor and technology industries. And I'm proud that Purdue and the state of Indiana are leading the way. Thank you again for letting me be part of this special day. God bless.
So we don't actually have anyone from Bell Labs here today, but two of our speakers worked at Bell Labs for some time. So we'll hear a lot about Bell Labs. All right, so to begin, we're going to begin by talking about what was happening before the invention of the transistor and then the invention of the transistor. And the key person from this area was a professor of physics and the head of the Department of Physics called Carl Horowitz. And I think he joined the physics department in 1928, and a year later he was named head of the department, and he's described as turning a department that was an academic backwater at that time into a powerhouse. And we're fortunate to have with us today Mike Manfra. So Mike is a professor of physics and also materials engineering and electrical and computer engineering. And he also directs the Microsoft Quantum Lab here at Purdue. But he also worked at Bell Labs for some time. And I think Mike is going to do two things: talk about what was happening at Purdue before the transistor was invented, and then about the actual occurrences of the invention of the transistor and Purdue's role in all of that. So thank you, Mike.
Thank you, Mark, for that introduction. And I am going to try to tell you a little bit about developments of semiconductors in general and the specific invention of the transistor at Bell Labs. The ordering may be a little different than Mark said. It's sort of a personal take on the matter. I realize I've only actually had two jobs in my entire life. The first half of my career was spent at Bell Laboratories, and the second half has been here at Purdue. And I have a great fondness for both, and learning more about how they interacted, sometimes collaborating, sometimes maybe being in a bit of competition, has been interesting. And I hope you'll indulge this sort of personal take. So yes, we're here. I would call it we're celebrating the birth of the transistor, December 16th, 1947. And as Mark's already said, it's often been called the most important invention of the 20th century. There's hardly an aspect of our lives that isn't impacted by the presence of, well, now integrated circuits, but starting out from the original transistor. And what you see here is a very primitive object, but the heart of it is a slab of germanium semiconductor crystal. And that's really at the heart of it, and this is something that both Bell Labs and Purdue had an active role in advancing, and I'd like to tell you a little bit about that story. Now, there's no doubt that this is a Bell Labs invention. The people responsible for this are shown here in this picture. Now, this is a little bit of corporate reality making or manufacturing. The people involved here are John Bardeen, Walter Brattain, and Bill Shockley. The man sitting at the bench and twiddling with the point contact probe is Bill Shockley. He was ahead of what was called the solid state physics group at the time, but this original invention and discovery was driven by the two people standing behind him, John Bardeen and Walter Brattain. And if you know who John Bardeen is, or he is certainly one of the giants of 20th century theoretical physics. He won the Nobel Prize not just once, but twice. Walter Brattain is a very skilled experimentalist, and Bill Shockley, of course, had many contributions to the physics of semiconductors and the technology as well. But these individuals, Bardeen and Brattain, are really responsible for the thing we're talking about today. And it also gives you a little bit of the flavor of how this actually worked. Bardeen worked hand in hand with Bratton over his shoulder, taking notes, and they worked hand in hand. One of the great theorists of the 20th century, and working beside an experimentalist. And I think if I can convey one aspect of Bell Labs and what made it unique, it would be this. But let's keep going. Okay. So this all occurred at Bell Laboratories. Now I'm jumping ahead several years, and this is the, oops, yeah, pointer's not working very well, but this is the Murray Hill campus. It was sort of the mothership for Bell Labs. This was sort of at its zenith in terms of size and scope. It's a sprawling campus, but the oldest part of the facility is called Building 1. In Building 1, at the very end of Building 1 on the 4th floor, is where the transistor was developed. And it just so happens that on the same floor, on the same corridor, I had a laboratory many years later. But I was always, had to pass by every day the plaque commemorating the invention of the transistor. And if there are some, for me, interesting stories about how I got my position and what were the hurdles I had to jump through to make it at Bell. But one of them was being told in order to hang on, I had to make something useful. And it turned out to be a transistor in a different material system. But anyway, it's a really fascinating place. I think, you know, from my perspective, it's the greatest scientific institution that's ever been. And it came about through very specific circumstances. And there's a great deal of literature on how this happened. And I recommend the books below, the Idea Factory. That's an overview of how Bell Labs came to be and the personalities and forces in the early part of the 20th century that drove it. Crystal Fire, getting to the subject of semiconductors and the invention of the transistor, is a great read and connects Purdue to Bell Labs. And there's also a book called Broken Genius, basically talking about Shockley. But you know, there's a really vast history. And in addition to producing much of the technology of communications and information science, this place has also produced a great deal of fundamental science as well, producing 9 Nobel Prizes over several decades. So it was really unique, and it's very formative in my thinking and approach to science, especially this, you know, this mixing in one pot of engineers, chemists, physicists, material scientists, all in one location, all thrown in together and needing to work in concert to accomplish goals. So, you know, it's Bell Labs did invent the transistor, and it's been documented actually in a series of papers that Shockley managed to submit back to back to back at the Physical Review by calling the editor directly and getting them published in a very short order, something we wouldn't think is reasonable to do these days, but nevertheless, he did. And you know, there was really Bardeen and Bratton were the drivers before this for the original point contact transistor. Shockley, of course, contributed enormously to the theory of semiconductors and junction transistors that came along later. You know, we, Mark, and others have had interactions with Bell Labs in the course of preparing for this this presentation, and had access to the Bell Labs archives. These are excerpts from the notebook of Bardeen and Bratton around that time, and these are courtesy of Ed Eckhart, who is the archivist at Bell Labs. And it is true, in those days, and even when I was there, we had labeled, numbered notebooks, and you had to write explicitly what you were doing, date it, and then if something important was going on, have a coworker authenticate it by signing it. And you can see in the days leading up to the 16th exactly, you know, which piece of material, germanium, that they were using, how they treated it, how they were preparing it, where ingot it came from. And going through these things in extraordinary detail is a really fascinating thing to do. So, there's, behind all of this, though, is the development of materials and their, gradual improvement, refinement, and both in terms of crystalline structure, purity, and doping. And now I do want to give you a little bit of the backstory. That's after the war. But what was really driving all of this? How did Bell Labs, and as well as a few select universities, get heavily involved? And the key was really what was going on during the Second World War. So radar, we often hear about the Manhattan Project and the triumph of big science and coming together. But I would submit that perhaps equally, if not more important, was the development of radar and the scale of effort and collaboration it took to accomplish that. So this was a collaboration between the British and Americans. In the United Kingdom, they had developed some very high-powered sources working in the X-band, the wavelength of a couple centimeters. But to develop the full integrated systems, they needed better detectors, and this is where the US really played a role. And so they had to make compact systems that they could load onto planes and ships, and they needed to be reliable, and they needed basically what you might call is a solid state diode rectifier. Sorry, I was looking for words, in order to in part of the demodulation scheme. So that's a little technical, but nonetheless. And it's also hard to realize how much science contributed during the war and how concentrated the efforts, or at Bell Labs, for example, 90% of the effort during the war was dedicated to radar and other types of activity in the war effort. And there were a few key universities as well to develop the radar project. It was driven out of MIT radiation laboratories, Bell Laboratories, General Electric, hopefully to manufacture things. But there were a few select universities in this group: University of Pennsylvania, MIT, and Purdue. And this was all driven by the military. But the reason Purdue was so prominent, played such a prominent role during the war, is their connection to building rectifiers and purification and improvement in germanium. And this was driven, as Mark has already alluded to, by Karl Horowitz, who basically, yes, took a backwater department and made it a powerhouse, hired his own people, ran it sort of as an authoritarian, but got results. So, he collaborated and competed. I don't know if compete is really appropriate, but in the radar effort during the war, Purdue was known for germanium and making it purer and purer, and getting control over doping that led to strong rectification, what we call high gate voltage rectification. And this, again, was essential to the radar effort, which was central to the battle over the Atlantic during the bombing of London. And so what Karl did was actually build up a very strong team. Names you may have heard associated with Purdue: Benzer, Bray, Whaley. They really pioneered purification and doping control in germanium. And again, this book, Crystal Fire, is a great read to see how they were working with the other groups, and samples were exchanged with Bell Labs, sent in both directions. Bell Labs, of course, was also working on purification of silicon and germanium within their own group. But during the war, there was a concerted effort to work together across many organizations in order for a common goal. And Purdue was really leading the way because of their work in germanium. And this is what had such a prominent role during the war in the radar effort that eventually, right after the war, led to the development of the transistor. So I think it's important to note how much was going on here at Purdue and how vital it was to the war effort. This was all driven, of course, by the military, and some of it, of course, was classified at the time, but it was really, Purdue was playing a leading role. And just to give you an example, you can see some of the publications from that era, or near, if there are any technical people, high inverse voltage germanium rectifiers, the dependence of resistivity of germanium on electric field by Bray, Benzer, the thesis of Whaley and Bray as well. It's all in this at the end of the war, early post-war era. And so when things actually got going at Bell Labs, they did become nervous. And this is after the war and developing the transistor. They were certainly aware of the quality of material and the efforts going on at Purdue. And Bardeen and Bratton in particular were concerned, well, we've got it, but they could do it too. And so there's a very interesting story about race for patents and information flow that reads very much a great deal of intrigue. So now I want to finish up that group, the solid state physics group that started with Shockley. The group I actually ended up with was called the Semiconductor Physics Department, was the direct descendant of that department. And our department head at the time was this gentleman named Federico Capasso, and he would often invoke calling us to rally the troops, that we're the direct descendants of the Shockley department, and we had to shape up. You may not recognize everybody here, but there's a younger version of me there as well. And what I hope is that by coming to Purdue and having this experience, to bridge that now at 75 years later, the characteristics that made Bell Labs great, but also were clearly here at Purdue for a long period of time. And I just want to show that semiconductors is still strong. Of course, this is a personal perspective. There's lots of other materials and lots of other groups all doing fantastic stuff. But in terms of the materials part, we still maintain a great deal of strength in modern semiconductor materials and purification. And there's a really strong effort here at Purdue, not just mine, across departments and schools, that is really admirable. And the capabilities that we have here and the talent keeps this going strong. And I just want to finish, a year or two ago, we made some discoveries of what you might think is fancy physics associated with anions and things. But in the end, it's nothing more than a transistor. It's just a fancy transistor that we made. It's in a system gallium arsenide, and they have very small gates and all of that. But at its root is an advance in transistors, the design of a transistor. And the fact that we can find physics in this type of development so many years later is really gratifying to me, and I think bodes well for the future here at Purdue and for the field. Thanks.
All right, thank you, Mike. That was great. So I'm just going to recollect back from my childhood. So I grew up in the 50s, and I was puttering around with electronics and paying attention to transistors. And there was this big debate all the time, tubes versus transistors, which one is ever going to win out? No, but it's really remarkable. The transistor was invented in 1947, and within just a few years, there were commercial products. So Texas Instruments was manufacturing transistors, and they went looking for someone who could help them build a radio out of transistors. And they found this company, Regency, located in Indianapolis. And this was actually the first commercial transistor radio manufactured in 1954, built right here in Indiana. You can see it's a little bit big. She's holding it in two hands. I understand that it didn't get great reviews. It wasn't, the audio quality Wasn't fantastic. But just a few years later, there was another transistor radio, and this one I remember as a kid. This was the Sony TR-63, a 6-transistor radio, and this was a commercial hit. And suddenly everyone had transistor radios, and this was the first commercial electronics product. It sold millions, and it was done by Sony in Japan. They called it a shirt pocket radio because you could put it in your shirt pocket. Actually, that wasn't quite true. This guy was a marketing genius. He had created his own shirts for his salesmen with pockets that were slightly larger than standard. But it was successful, and he was a commercial hit. Now, as I said, I remember reading my ham radio magazines, and there was always this debate, and which one is going to win out. So these are the kinds of stories I would read in my ham radio magazines. The vacuum tube people weren't giving up. They were doing everything they could to make vacuum tubes small. And as you can see here, they've unveiled, this is a Nuvista, who is this, RCA probably. They've unveiled their latest transistor to keep them in the race with, their latest vacuum tube, to keep them in the race with transistors. And I remember another ad with a picture of a very small tube, and the title of the ad was, "Who says transistors are small?" But it didn't take very long before people realized that these devices are really they're going to win out. This is an interesting fellow. Does the name Fred Terman ring a bell to any of you? So he's sort of famous for two things. He's often called the father of Silicon Valley. Hewlett and Packard were his students. He convinced them to come back and start a company. And he sometimes shares that credit with Bill Shockley. The other thing he's famous for is he's usually credited for making Stanford University what it is today. It was sort of a good university before he came, and he spent 40 years there as professor, department head, dean, and then provost, and made it what it is today. He's a native-born Hoosier, so there's an Indiana connection here as well. And he gave a speech in 1960, and by 1960, a few people had figured out that there is a new electronics, and it's not vacuum tubes. It's characterized, it lives close to the frontiers of science. It requires a high level of technical competence. It grows by the development of new products, like these transistor radios, and it's characterized by the transistor and other devices. So he really saw the future. Actually, the point of this trip is he was coming back to his roots in the Midwest, talking to his colleagues and saying, while you're focusing on educating students to go into the vacuum tube industry and make televisions, and you're making a big profit there, the future is transistors, and it's happening on the West Coast and the East Coast, and this is what you should be paying attention to. Okay, so we're going to switch gears and have another talk now. The point contact transistor got things started. Shockley's bipolar junction transistor was a much better transistor, and that's what was used in the Sony device and things. But the transistors that the billions and billions that we find in our smartphones and our laptops and everything else are not bipolar transistors. They're a different kind of transistor. And that transistor was also demonstrated for the first time at Bell Labs. And there's an interesting Purdue connection here as well. That was done in 1960 by a Purdue alumnus, Mohammed John Attallah. He was actually a mechanical engineer, and it's remarkable. He learned a lot of solid-state physics very quickly at Bell Labs, and was able to, you can see his history. He spent some time at Bell Labs. We're going to hear about his work at Bell Labs in a minute. Then he went on, I think he was the founding director of Hewlett-Packard Labs, spent a short time at Fairchild Semiconductor, and then started his own companies. He received a Distinguished Engineering Alumnus Award here and an honorary doctorate from Purdue. So we're going to switch gears now, and we're going to hear from Professor Alam about a little bit about what Mohammed Attallah did and why it was significant. Ashraf?
So next time you buy a powerful computer and marvel at its speed and the colors and the displays and everything that goes with it, you may wonder that where the power comes from. The power that really comes from an integrated circuit built within it, on the size of maybe two of my thumbs, containing more than 100 billion transistors. Now, 100 billion is an astronomically large number. 100 billion is the number of stars in our galaxy, and 100 billion is the number of galaxies in the known universe. That is how big 100 billion is. And in fact, some of these computers would be able to compute in a week what the supercomputers of 1970s would not be able to complete in a billion years. So actually, this is a culmination of almost 60 years of progress. And within these 60 years, the density of the transistors essentially doubled every other year or so. And many of these things this progress is called a Moore's Law. Now, we not remember the Moore's Law per se, except that maybe during the Christmas time, you would have maybe wanted an Apple PC, IBM PC, or maybe a Power PC, maybe successive generation of the Pentium computers. And essentially that led to this 100 billion transistor that powers our computers today. But what is interesting that this trend was first identified and coined, this name Moore's Law was first coined by Carver Mead, a Caltech physicist and engineer. And what is interesting is that how the trend came about. In fact, what happened in 1965, Gordon Moore, then at Fairchild, and subsequently one of the founders of Intel, was asked to speculate the state of integrated circuits 10 years afterwards, so from 65 to 75. What would happen in the next 10 years since then? So naturally, he went back and looked at the number of progress of electronics within the last few years. And for every year, he would look at the number of transistors produced at that time until 1965, and plotted in a curve and identified this trend that there would be a rapid doubling of the transistor numbers every 2 years or so. And that's what became the Moore's Law subsequently. But the curious fact is that the Big Bang of the Moore's Law is not at 1947, but rather at 1959. That's very interesting, because the story you just heard would say that the transistor and this beautiful progress leading to the computers that you have today should have started in 1947. You just heard about the stories of Purdue and these three giants essentially creating the transistors 75 years ago today. But actually, the transistor, this big trend that we now know as Moore's Law, started actually based on a different type of transistors. And this different type of transistors is slightly different in the sense that it has two contacts. Electrons essentially, or the charges here, is controlled by a gate separated by this insulator. This insulator was impossible to fabricate before 1959. And that made all the difference. So Muhammad Atala, had he lived today, he would be almost 100 years old. He was born in 1924 in Port Said in Egypt, and he was educated in Cairo University. And as the Second World War just completed, or just was getting over, he came to America, to this West Lafayette campus, to complete his PhD, master's and PhD. And as you can see, he did so almost exactly at the same time as Ralph Bray did. Ralph Bray finished in August. He finished in June of 1949. I'd assume that in a small campus like that, at least at that time, they must have crossed paths many times because they were both graduate students exactly at the same time. His thesis, as Mark has already mentioned, dealt with mechanical engineering topic, and specifically when you have a squared diffuser, something that allows the gases to diffuse at subsonic speed, he essentially worked out the theory or the solution of Navier-Stokes equation to know how the gases hug the edges of the diffuser. Subsequently, he went to, he joined Bell Labs, and for first 6 or 7 years between 1949 and 56, he worked on the reliability of electromechanical relays, nothing to do with semiconductor physics. However, just like electromechanical systems have a notorious reliability problem, the transistors that were being created at that time were equally notoriously unreliable, because these things, when they are exposed to outside ambience, the various contaminants essentially would make these transistors reliable one day and not functioning at all then the next day. One batch is good, another isn't. So when Atala was asked to actually solve this problem, he went back to his thesis topic, diffusion of gases, and at enhanced temperature had oxygen reacting with silicon to create a skin that will protect all the electronics underneath. This is the genesis of the integrated circuit, highly reliable, highly stable integrated circuit. And remember that the MOSFET also needed that gate oxide. So within a year or so, that gate oxide will also be formed, and the first MOSFET will be demonstrated. What is remarkable, and that I still am a little bit jealous, that just after spending 3 years on physical chemistry, learning quantum mechanics, statistical mechanics, and all, he would write papers that would explain the improvement related to this thermal oxidation in a level of details that is still today a marvel to me. So if this was sort of the beginning of the Moore's law, this rapid expansion thereafter, the beginning of the Moore's law and the few points that Gordon Moore plotted in order to anticipate this trend, is also a date to the Apollo program. At that time, the integrated circuits were very expensive. A 6 transistor integrated circuit cost about $100. People could easily make circuits by hooking up transistors at a fraction of that cost. However, Apollo program needed something special. During takeoff and also re-entry, the violent shaking of that of the whole spacecraft required that the electronics be extremely reliable. And mechanical systems simply couldn't do that. And an integrated system based on this Atala system was able to do so. By the 1970s, the Apollo program would buy almost close to 1 million integrated circuit, and almost 2/3 of the supply in Apollo 11 of the integrated circuit came from a single company, which is Fairchild. So this man that has landed on the moon, there's much to be said about the integrated circuit making that possible. And indeed, the distinction between the Russian system, which did not have an onboard computer, is the main distinction that allowed the Apollo program to succeed. So the story I see here is really an inspiring story. In the beginning, I was sort of somewhat disheartened to learn about Atala, that he's a mechanical engineer. However, with no background, and then he comes out of nowhere and makes this technology possible. But in retrospect, I realized that had he not known about the diffusion physics and that he learned in mechanical engineering, this invention might not have been possible. The second thing is also that in terms of not only scientists and engineers, when you think about a phone, any phone that we have, within the phone lives essentially the dreams and discoveries of all scientists, whether it is Democritus or Dalton or René Descartes or Boltzmann or Einstein, everybody's essence, they may not have met in life, but their essence of their understanding lives on and makes this technology possible. The second takeaway I have from this story is that this is a uniquely American story. Atala came from Egypt. The other Kang came from Korea. Bray was a Russian immigrant. And they all came and worked in an American institution like Purdue University or Bell Labs that offered them opportunities to work together and make this remarkable invention possible. Where else but in America you can expect this type of collaboration to happen? Atala for me is also a model of engineer, a restless visionary and engineers, because Atala not only did transistors, he worked for a few years. The Bell Labs were not interested in integrated circuits, so he left. Then he did 3.5 transistors at HP, and then he did LED in Fairchild. And then in 1972, when a banker asked that securing the transaction among the banks is becoming difficult, he completely left semiconductors, went into cryptography, and invented the ATM machines that we use every day. By early 2000, 98% of all bank transactions in the United States were being secured by these Atala machines, these PIN machines that we generally use in the banks and all. So I think this ability to go from one to another based on the timely problems and offering timeless solutions is also a model that I hope that we'd be able to emulate. And finally, there is this work goes on at Purdue on the same tradition. There is all this silicon carbide transistors in Tesla cars and electrical cars. There's gate-all-around transistors, negative capacitor FETs, tunnel transistors, all of these things that are still happening so that tradition lives on. And finally, I'll just end with by saying one thing, that there is no statue of Atala or Bray here at the campus. We see one for Neil Armstrong. But every time we pick up your cell phone and talk to somebody or check an email, the memories of these giants, Purdue giants, essentially live on in these majestic machines. That's all I had. Thank you.
Thank you, Ashraf. So we're celebrating the invention of the transistor, and a lot of this is highly relevant to us here at Purdue. So Ashraf mentioned the Apollo program, and here at Purdue Space, we talk about space all the time. So Neil Armstrong, Gene Cernan, both are alumni, both distinguished engineering alumnus, honorary doctorates. And as Ashraf mentioned, a key advantage that the US had in the space race was that we had transistors and integrated circuits and onboard computers. So we're going to switch gears just a little bit. We're very fortunate to have Dr. Katya Babinsa-Sava from the Department of History, who is going to tell us something about the history of what was happening during this period of time. So Katya, turn it over to you.
I am a historian, and I think humanities people and STEM people approach talks a little bit differently. We kind of tend to write and then read. So that's just my disciplinary quirk. I'm going to look at my written text as I'm speaking. I hope it's okay. Well, it's a real pleasure to be here and to be a part of this anniversary celebration. As I just said, I'm a historian of science and technology, and in my research, I am primarily interested in the history of computing. And historians are also interested in establishing historical patterns. In other words, we study how the complicated chains of events are triggered by scientific discoveries and technological innovations. And given my interdisciplinary background, today I would like to zoom out of the early history of the invention of the transistor, and instead I would like to situate this technological innovation within a broader context of American 20th century science and technology. So I'm arguing today that this small and quite unappealing to a lay person's eye technology really helped significantly transform science and technology in the early 20th century. And in particular, I will focus today on the impact that the invention of the transistor had on space exploration in the United States in the mid-20th century. I'm sure you can already tell from my slides that I will be focusing on the role of the transistors in the Apollo 11 mission. And Ashraf kind of spoiled my talk a little bit by saying that the microchip was crucial for the Apollo 11 mission, and that's how the the Americans beat the Soviets in the space race. So yes, true. But also I decided to focus on the Apollo 11 mission because yes, there is this one alumnum, Neil Armstrong. He was the commander of the mission, and you can see him on the slides. You can even see an excerpt from a local Lafayette newspaper, actually a cover page of that newspaper from 1969 that calls him "Produce Columbus." And yes, when we look at the Apollo history, we also see significant changes that were happening in American electronics and computing in the mid-20th century. On this slide, you can see a crucial element of the Apollo 11 mission, a lunar module called Eagle like a bird. As the crew approached the moon, the lunar module undocked from the main module and carried Neil Armstrong and Buzz Aldrin to the moon surface. The third astronaut of the Apollo mission, Michael Collins, stayed aboard of the main spaceship, which remained in orbit around the moon. So bringing a spacecraft to the moon required performing an enormous number of astronomical measurements. These measurements also needed to be performed in real time during the flight. Human brains just don't have the capacity to analyze and act quickly upon the rapidly changing data produced during a manned lunar mission. And by the 1960s, it was already quite an accepted idea that calculations, especially such complicated calculations that were required for the Apollo mission, should be outsourced to computers. As was already mentioned previously, the anti-aircraft guns and missile guidance systems relied on calculations performed by computers. So if computers could guide a missile to a target or track the movements of an enemy airplane, they could probably guide a spacecraft to the moon. But the problem was that the computers that existed in the 1950s and the 1960s were enormous in size, they consumed a lot of power, and they didn't have the required computational capacity. And they were enormous in size because they used the vacuum tubes as switches in an electrical circuit. And by the way, I didn't know that there were these smaller vacuum tubes. I learned about this today. But as far as I know, computers used the vacuum tubes that were the size of a contemporary light bulb, and therefore computers really were the size of a room. You couldn't put such a huge computer on a spaceship. It was just impossible. So the computer that needed for the Apollo mission needed to be dramatically different from everything that existed. And the computer that was required for the Apollo mission just simply didn't exist in the early 1960s. It needed to be invented. This next slide shows the Apollo guidance computer and its main designer, Eldon Hall. By responding to the technical requirements of the Apollo mission, Hall and his team managed to set a new trend in computing technology. The computer that you see on the slide was the state-of-the-art technology of that time. It weighed about 70 pounds, which of course by our standards is huge and heavy, but by the standards of the 1960s, it was a really tiny computer. And its invention began a transition between people bragging about how big their computers were to people bragging about how small their computers were. And I'm sure that for the people in this room, it's a well-known fact how Hall and his colleagues managed to make the Apollo computer smaller. The key to a powerful yet smaller computer was in placing transistors and other circuit components onto a piece of silicon. In other words, the key was in the building of the silicon chip. The transistors, thus, were really the key to creating the Apollo guidance computer. As I mentioned, the computer calculated the course to the moon, but I should mention that it relied on the measurements performed by the 3 astronauts. The 3 people that were on that spacecraft did not just lounge there until they got to the moon. They were really communicating with this system all the time. The computer also controlled the many physical components of the spacecraft. It could communicate with 150 different devices within the spacecraft, which was an enormously complicated task. For example, it communicated with the landing radar, another complicated piece of electronic equipment, which provided the computer with altitude measurements and tracked the lunar module's speed as it approached the landing. This next document I acquired at the Purdue Special Collections and Archives. Purdue is famous for its School of Engineering. It also has really fabulous archives which document the historical developments in science and technology in which Purdue participated in direct or tangential ways. So in the 1970s, the journal called Astronautics and Aeronautics published a series of articles which responded to the following question: what made Apollo a success? And one of the articles explained that the technology that contributed to the controlling the trajectory of the spacecraft was key to the success of Apollo. And if you look at the list of the technologies on the right, you can see all those elements that were in touch, that were communicating in real time with the main computer invented by Hall. And this is also from the archives. It's a cover page of that journal where this series of articles were published. The cover says, "A planetary navigation, the new challenges." And this cover really caught my attention because I think it signifies how our understanding of computers really changed with the Apollo mission. Computer really became a key, crucial technology for space exploration, a scientific instrument without which a space exploration wouldn't be possible. So I told you that I'm a historian of science and technology, and we're always obsessed with historical patterns. So I'm sorry I can't talk about the 20th century without looking back at the 18th century. When I lecture on the scientific revolution, I show this painting by Arthur Davis. This painting features the family of Robert Boyle. But the most interesting part on this painting are not humans, but instruments. These 3. Maybe somebody recognizes those, no? Okay, I won't be tormenting you. I'll just tell you. This is the air pump, a sextant, and a telescope. These three, according to this painter and his contemporaries, signified the keys to the objective understanding of the natural world. And today I suggest that the computer that was on board of the Apollo mission, and which was made possible because of the transistor, really became a technology, a key scientific instrument for expanding the horizons of our world and allowing the humans to get access to those parts of the world that were inaccessible to them previously. Not only the digital computers that were used for the Apollo mission were crucial for understanding the space, but later on, because of these technologies, we gained a better understanding of our own planet. Earth sciences and planetary sciences really evolved from the space explorations that were happening in the 1960s. And as I hopefully convinced you, transistors were really key to this important stage in the history of science and technology. Thank you.
Thank you so much. So I'd like to thank our three speakers for three different and three wonderful perspectives on the transistor. So just to wrap up a couple of remarks. So back to Fred Terman. If you read the title of his speech at the electronics conference, it was about education, a basic component of the new electronics. And he made the point, he was making a point in this speech, is that the success of this new technology, the most critical factor is education. Well, about the same year, there was an educational initiative that was launched. And it was a group of people, some were from industry and some were academics, and they realized that the future is transistors and semiconductors and integrated circuits, but all electrical engineers are being taught how to design vacuum tube circuits because there are no textbooks for transistor electronics. There's only Shockley's book, Electrons and Holes and Semiconductors, which really isn't an engineering textbook. So they got together and they produced a series of, I guess, 7 low-cost paperback volumes that made it possible for people to begin to incorporate this into their existing classes. And this just had tremendous impact. So you could teach people how to design transistor circuits. If you read these books today, they still sound modern because they also produce the intellectual framework. This is how we think about solid-state electronics and how we still do. So they had tremendous impact. So, you know, we think we're at a similar time today. Ashraf talked about Moore's Law. There's a lot of debate about the end of Moore's Law. You know, we're getting close to the point where we can no longer advance electronics by making transistors smaller and putting more of them on a chip. But I think none of us have any doubt that transistors or that electronics will continue to advance. Most of the public won't realize that something has changed. But we in the science and engineering communities will have to figure out how to advance electronics in different ways, different than we have been doing from the past. So there is a need to bring some new ideas and fresh thinking into the curriculum. So today we're making an announcement of this new lecture note series, we're calling it. This is a partnership with World Scientific to produce a set of low-cost volumes, short, that can be inserted into existing courses that people can use to bring new ideas and new ways of thinking to our students. And we're hoping that it has impact that's similar to the famous Seek Notes. Now, you'll notice we have a number of authors here. How many do we have? 1, 2, 7? All Purdue authors. It won't be a Purdue series, but we're starting with a group of Purdue authors, so you can see their names there. So those of you that are in the audience and are thinking about writing a textbook, I know this can be very intimidating to write a traditional 500, 600, 700-page textbook. It can take a long time. So really, we're aiming to lower the barriers here and to get you started. They're short, produce camera-ready copy. You know, there is a large amount of high-quality PowerPoint material out there. And many of you, they have developed and refined this, you know, teaching courses many, many times. This will all be lost if it isn't put into the archival literature. The next 2 volumes that will be published consist of PowerPoint slides with text. So it's a very easy way to get started. And eventually these may evolve into full-length textbooks the way the Seek Notes did. Now, in an act of shameless promotion, I'm going to show you volume 1 in this new series.
By whom?
It's appropriate for this day. Volume 1 in this series is about transistors and new ways of thinking about transistors. So I hope you'll think about whether you might be able to contribute to this series as well. We're really excited about it. And it will be, you know, all kinds of different topics for advancing technology, including quantum technology, Vlad. So think about doing this. All right, so we're having a reception out back. I hope you will all stay for that. The closing remarks, we hope, will be by President-elect Meng Chang, who got his meeting ended 5 minutes ago, so that we're hoping that he will get over here and be able to give some closing remarks. Please, thank you for joining us this afternoon. Stay, talk to your colleagues before we all get away for the holidays, and spend a few more minutes with us. Thank you all for being here.